Alright, class, so we've learned about velocity, we've learned about acceleration, we've learned about distance, which can sometimes be the height, and that's about time, and in time as well. Today we're going to add another variable called force. And force is something that you can think of that includes how heavy something is and how fast it's speeding up or slowing down. And the official definition is an actual equation, but I'll go ahead and repeat that. So think of force as how heavy something is and how fast it's speeding up or slowing down. Not how fast it's going, how fast it's speeding up or slowing down. And speeding up and slowing down can be reworded as acceleration or deceleration. And this is a physics problem that is in 0-1 forces that'll demonstrate to you what a force really is. The question says, what net force is required to bring 1,000 kilograms of a car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? So we want a car to slow down, but we want to know how much force is required to make it slow down. So every second, it's going to get a little bit slower. That's different than how fast something is going. And it's a 1,000 kilogram car. So we haven't really dealt with mass in any of our physics problems until now because we have a bigger, a deeper understanding of how certain variables relate to one another. Last week, we learned a topic of velocity equals, distance equals velocity times time. Remember that triangle? Velocity is at the top, and then, I just butchered it again. Distance is at the top, velocity and time is at the bottom. Now I bring that up only because there's another triangle here that you can use to help you remember which equation equals what. Instead of x equals velocity times time, this new topic is force equals mass times acceleration. You can also use the triangle to explain that acceleration equals force over mass. And you could also use this triangle to explain mass equals force over acceleration. So 3 equations from one triangle. It should be helpful going forward, the same way x was at the top of a triangle where velocity times time equals that. Now we're going to try to find the force. That's what the question's asking for. How heavy something is and how much it's slowing down. And that means we're going to use the top formula. F equals ma. Now we have m, which is mass, 1,000 kilograms, but we don't have a. So in order to calculate a, we have to use a second equation and then plug it into the first equation. So this is the first equation on the left, second equation on the right. Now ignore the red part first because that's just how I cancel out variables. A is in this equation. So is velocity and so is distance. Velocity is given to us. It's 100 kilometers per hour. And distance is given to us 55 meters. That's why this equation is going to be helpful. All we need to do is find A. So I'll give you a second to copy that down. While you copy that down, I'm going to explain why velocity final is going to be 0. The problem says what net force is required to make the car to rest. So velocity final will be 0. Velocity initial will be 100 kilograms per hour, and your x is 55 meters. But we're trying to solve A. So let's take the steps to solve A. Square both sides, and what's left over is Vf squared equals Vi squared plus 2a delta x. Delta just means final distance minus initial distance. But our initial distance is 0, So you don't even have to consider doing final minus the initial distance. Just write the final distance. Now, a is still not by itself, so we're going to subtract both sides by vi squared. And what's left over will be vf squared minus vi squared equals 2a delta x. And the reason why we didn't divide by 2x earlier is because you have to go in reverse of order of operations. Usually when you do a math problem, you do multiplication and division first, and then addition and subtraction last. But when you're trying to cancel stuff out, you do addition and subtraction first, and then multiplication and division last. So we subtracted vi squared from both sides, and now we're going to divide and undo the 2x. And what's left over is going to be the equation for acceleration. Once we find acceleration, we'll plug it into our first equation and then have the force required to stop a car. That's 1,000 kilograms. See everyone writing, except for one. Let's list out the variables that we're going to plug in. V sub I is going to be 100 kilograms. X is going to be 55. And then final velocity is 0. But we have to look at the units. Meters per second, those are not the same as kilometers per hour. So, just like we did a month ago, we're going to convert units into other units. And the way we do that in physics is to multiply it by a fraction. This is how you cancel out kilometers and hours. I rewrite the units as 100 kilometers over 1 hour. And then I multiply it to a fraction that also has hours and kilometers. Here's the first fraction. 1,000 meters over 1 kilometer. Students from period 1 asked, where did I get the 1,000? Well, in every kilometer, there's 1,000 meters. So that's why this fraction will be useful, because it's the same thing as 1 over 1, but it helps me eliminate the km. That's where the red part comes in. Now I'm still stuck with hours. So I need to multiply it by another fraction that eliminates hours. Hours needs to be in the numerator, and then seconds need to be in the denominator. So here's my second fraction. 1 hour over 3,600 seconds. Where did I get 3,600? That's just how many seconds are in an hour. And this fraction allows me to cancel out the hour that's in the beginning of the given value. Now you're going to carry everything over and do the math. I'm going to have a student do the math for us. I'm going to call on Carolyn. Grab a calculator and give me 100 times 1,000, hit equals, then divide it by 3,600. $100 times 1,000, hit equals, and then divide by 3,600. 27.78. And that's meters per second, no longer kilometers per hour. And now we can plug it into our acceleration equation, and then plug that into our force equals mass times acceleration. We're going to plug in our values. 0 is our final velocity because the car needs to be at rest. 27.78, Carolyn helped us find that. That's velocity initial squared divided by 2 times 55, which is the distance the car is going to travel. I'm going to have a student help us do the first part. Angel, grab a calculator. Is there one nearby? Slide. There you go. and do 27.78 squared. Don't include the negative in this because it's outside of the parentheses. 27.78 squared. Try it one more time. 27.78 squared. You got the same thing? Try one more time. 770, the whole thing. 0.73. Good. And can you do 2 times 55 for us? 110. Now let's do the last step. Michael, grab a calculator and put in negative. Notice we saved the negative because it's outside the parentheses. Now we apply negative 771.73 divided by 110. Try one more time. Negative 771.73 divided by 110. Zero. Say the whole thing? Rounded. Because it says 1.5. So it's negative 7.02. Okay. Now this isn't our final answer. We just solve for acceleration. That is our A in the F equals ma. So let's plug in our last step. F equals ma. And we're going to plug in 1,000 for our kilogram of car. And then we're going to plug in negative 7.02 for our acceleration. And this student will do the calculation. Juan, grab a calculator. What's 1,000 times negative 7.82? 1,000 times negative 7.02. Say the whole thing. Negative 7,020. The units are called newtons, but that's not our focus. Our focus is how do you calculate the value from this equation all the way to that.